Good evening, everybody watching online. We will be starting in 5 minutes. Please bear with us. Thank you. Good evening, everyone. Before we begin, I've got some brief housekeeping notices. There are no planned fire drills, so if you hear the alarm, please leave the room, either by the door at the back that you came through and through the main entrance, or through the illuminated fire exit to my left. The assembly point is just beyond the building outside 42 Baswick Street. We have a photographer here this evening, and photos will be made available online. If you don't want to be featured in the photos, please inform myself or a member of the events team. Finally, please note that photography or recording is not permitted during the presentation this evening. Thank you.
Thank you, Louise. On behalf of the Institution of Structural Engineers, I welcome you all here this evening to this special event and the presentation of this institution's most prestigious award, which is given to an individual for exceptional and outstanding contributions to the advancement of structural engineering. I offer a particular welcome to James' family, his colleagues and his friends who are here this evening to support him. As you might expect, gold medalists are a very special group of people. And in its 111-year history, this institution has only awarded 53 gold medals over the course of that time. Undoubtedly accomplished as structural engineers, it is, as Tim Eibel, a former institution president, observed, creativity sets gold medalists apart from the rest, and that's not exceptional, that's no exception this evening. And our 2019 recipient, James O'Callaghan, richly deserves to join that distinguished list of recipients recorded here on the plaque on my right-hand side or your left of the screen. James O'Callaghan is a fellow of this institution, was made a fellow of the Royal Academy of Engineering in 2018, and together with Brian Eskerley, founded Eskerley O'Callaghan in 2004 with a shared vision of a structural design practice that truly integrates engineering and architecture. They've been wowing the world ever since, and beyond their head office in London here, with bases in New York, San Francisco, Paris, Shanghai and Hong Kong. Famous for their collaboration with Apple, the brand's global flagship stores occupy some of the most extraordinary glass structures ever conceived. James is no stranger to awards, and in 2017 he was awarded the Phoenix Award and Glass Person of the Year, recognising an outstanding contribution to the international glass industry from the fields of science, production and education. James was the recipient of the UK IAPSE Mine Medal in 2016, awarded to an individual engineer for excellence in structural design, and in the same year the firm was named Engineering Consultants of the Year in the Buildings Awards. He has twice received the Queen's Award for Enterprise, for Innovation in 2010 and International Trade in 2018, as well as recognition in this institution's annual structural awards. You will therefore agree that I am sure that we are in the presence of a very special person and a very special occasion this evening as we listen to James's gold medal address. The rest of this evening will proceed unannounced. After James has delivered his address, it will be my great pleasure to present to him with the gold medal and the gold medal certificate, following which Ian Firth, a former institution president, will offer a vote of thanks. At the conclusion of the formal proceedings, I invite you all to join us for a drinks reception in both the library and the members' area upstairs. Ladies and gentlemen, the citation for the 2019 gold medalist reads, "An institution gold medal is to be awarded to James Dominic O'Callaghan in recognition of his internationally leading expertise in the creative and ambitious use of structural glass." Please now give a warm welcome to James O'Callaghan.
Thank you, good evening. Slightly put off there, my daughter just found out that my middle name was Dominic. So, hey, thank you, Joe. A glowing school report. I have a lot to live up to, no pressure. Skip through that. So good evening, everyone, and thank you all for coming and for giving up your valuable time on such a beautiful evening. And thank you to all those who are watching this being live streamed wherever they are in the world. It is a great honour to be awarded the gold medal, and while I owe thanks to far too many people, I only have time for a limited few. Firstly, I would like to thank those on the award committee for inviting me to be the recipient of this award. It is a truly humbling to be recognised by my peers for the contribution to this discipline, which we are all so passionate about, and to be recognised amongst the great engineers who have received this award in the past, many of whom are the very reason I chose to be a structural engineer. Many thanks to the past presidents Tim Eibel and Ian Firth for all their enthusiasm and encouragement. They have been fantastic supporters of the work we have done over the years. There are many incredibly brave, bold clients, architects, engineers and makers that I've worked and collaborated with along the way. But a special thanks to Bolin Sawinski Jackson Architects, Foster & Partners, Mark Adams and Martin Francis for their incredible opportunities that they have entrusted me with. Thank you all to my co-directors and staff, past and present, at Eckersley O'Callaghan, who've supported me and supported the growth of our practice around the world while ensuring our team is delivering the very best of service it can. I owe a special thanks to Stefan Bailing, and for the senior partner at Foster & Partners, for being the protagonist he is and stimulating the ideas in my head that have helped bring to life some of the most incredible glass structures and projects we've done and worked together over the last 10 years. And to my most influential patron, and for the last of my 15 years, Apple. It goes without saying, without them, I would not be here today, without their vision, support, and that they have provided me. And to my family, who have always been supporting me through my journey as an engineer despite the extensive travel and often resulting absence. Specifically my wife, for the polite enthusiasm she shows when discussing glass connection mechanisms, all of which she finds mind-numbingly boring. And to my children, who join me here tonight, having been bribed with chocolate. Chocolate, another material with incredible properties. We all have a reason why we chose to plough this field of engineering, and often there is at least one person who has inspired us in the past, often a teacher or perhaps an experience. This inspiration is fundamental to our discipline in thriving and remaining relevant in the future. My journey and adventures with glass as a structural material is one that results from inspirations and influences, so I wanted to touch on these tonight. Curiosity has driven my interest in glass, and I believe curiosity should be the fundamental driver of engineering itself. It is the curiosity we must foster and encourage in the engineers we support and inspire. We all have this duty. Ideas are fragile. They must have their moment, however crazy and crazy they may seem at first. Innovation is often associated with our work. I have learnt along the way that innovation is more typically an iterative evolution of solutions. The success depends on the landscape of relationships that are developed with clients and collaborators alike. It is about having a common goal and an aligned focus. Perhaps the most important relationship is that of your client, your patron. Ideally, reaching an understanding where you are given the latitude to experiment and propose novel approaches to real buildings. That knowledge that you are supported, that someone is holding your hand as you walk over the precipice of a solution is vital to encourage brave and bold approaches. While I recognise that is unfortunately too rare, I have found that it is trust that you can build over time, and the best things come when that trust is implicit. I have found that it is people that I work with that inspire me the most and provide me with the fuel that I need to apply my challenge at hand. Throughout my journey, I've had to be brave, be bold, and be confident to ensure that those I work with have faith in the ideas and innovations. You have to believe, and you have to be seen to believe. I aim to conclude by looking at what engineering looks like in the future, or is looking like, the challenges we face and the opportunities we can embrace, which only go to reinforce how wondrous engineering is. We're at a point in time where the technology revolution is forcing us to redefine our relevance. This will become something that we'll need to collectively address as our traditional role and services evolve. I think of it as an opportunity for us all to make sure we remain relevant and continue to be pivotal in engineering design. My road to structural engineering started with a bridge. I was 10, and my uncle lived under the construction of the Humber Bridge, pretty much directly under that far pillar. I was taken by its scale, fascinated by these giant forms and how these giant forms were orchestrated. Back then, I found it wondrous. Now I still think of bridges like this pure engineering efficiency. How do they do so much with so little? Its efficiency led to its elegance, and by their very engineering nature, therefore sustainable. During my early teens, I started to understand what fascinated me more about mechanics. I was a keen member of the secondary school engineering club, and the teacher responsible for us was an avid model train buff. He managed to persuade the school to fund for materials for a fully operational miniature steam train, and had us all make its parts, some of which required some quite detailed machining. It was fascinating to see how this engine gradually grew as each small bit was machined to precise prescribed tolerances. I loved this attention to detail, and I am sure that my love of detail was heavily influenced by this experience. It was through this same club in my later years at secondary school that the most influential opportunity came my way. I was part of a small team of students that were visited by a structural engineer from Arup. Unfortunately, I can't recall the engineer's name, which still vexes me now, as I have a lot to thank him for. He came and talked to us about structural engineering and what it was about. He set us a project over a period of months, which was to design a travelling, demountable exhibition. It was, of course, around that time that this collaboration between Renzo Piano and Arup, specifically Peter Rice, had developed the IBM Pavilion, a project that completely gripped me as I began to understand it. The project was so exciting to me then. We sketched out the design, and we learnt from what we'd been taught, and we trotted off to Fitzroy Square and used a computer at Arup to calculate the frames and establish the member sizes. We were taken on a tour of the recently completed Lord's Mound stand with fabric umbrellas and learnt about this relatively new typology of fabric roofs, all of which seemed so fresh and creative to me. We went back, we built physical models and presented them schemes to Arup, and at the end of the project were judged. And although I don't recall being the winner, it was amazing to see and feel what it was to work in engineering, to tangibly see what can be done through the process of design. This was the single most influential event in my education that ended up making me focus on structural engineering as my career choice. It illustrates the power of a relatively simple intervention in encouraging younger people to be engineers. As I studied my A-levels, I was introduced to Bill Bailey of Bailey Johnson Hayes Consulting Engineers. I was fortunate enough to be able to work in their office during my holidays. This continued with a sponsorship through the university days in Manchester. Bill was an excellent mentor. He gave me the time and shared his experiences about the fundamentals. He helped shape my intuition. A man of strong values, pragmatic engineer with wide shoulders to take on any challenge and not to be afraid of it. So thank you for being here, Bill, and thank you for your wisdom and experience. In 1995, I started working for Tim McFarlane at Dewhurst McFarlane and Partners. DMP, as it was known then, was an amazing practice in many ways, and many of today's engineering practices in London and further afield have been formed by the ex-alumni of DMP. It was a hotbed of creative engineers working with some of the best architects in London. As a young engineer, I suddenly felt I was in the right place, doing the right type of work that I could relate to, and my interest spiked. Tim was the pioneer of structural glass. It was his collaboration with Rick Mather on a residential project at Keats Grove in Hampstead that put the concept on the map. It was Tim's approach to engineering of this uncharted material that really inspired me. He would take everything to first principles, given that there was no landscape of codes or guides to use for the use of glass structures at the time. He would use old, tattered engineering references, pieced together with experiments and testing, all of which mapped out a safe approach to design of glass structures. Finite element analysis was in its infancy and not that accessible to small engineering practices at the time. With his collection of data and test results, and he and those at DMP realized projects such as Keats Grove, Broadfield House, and ultimately the Yokracho Canopy in Tokyo. Each project built on its predecessor, stretching the confidence in the material's behavior each time. It was through this I began to understand that innovation is a journey, an iterative process that needs a certain amount of time to soak in and feed back before the next development evolves. My first project of significance with glass was actually a very large-scale project in Seoul, a tower headquarters for Samsung Life Insurance. I specifically remember a late summer day in 1997 when Tim walked through the office and asked anyone if they wanted to go to Seoul to work on a project for 6 months or so. Without really thinking, my hand shot up and my eagerness won me the opportunity. I specifically remember going home that evening, looking on the atlas to find out exactly where Seoul was in the world. Geography was not my ace subject, and Google hadn't invented the Earth yet. Dispatched to Seoul in late 1997, I had a fairly steep learning curve to negotiate, all incredibly valuable lessons. Using a modified version of the connection detail concept developed for the Eurocratio canopy, we developed a design for a complex structural glass facade. I had to apply the basics of glass design, analyze with very limited software, but most importantly, taught myself CAD. It was this, perhaps the latter, which turned out to be the tool that set me free. While I had always been a reasonable sketcher, the accuracy of CAD became an essential tool when starting to detail. It's the only way to truly understand the tolerances and therefore the only tool you can really use to refine and refine details, which is so critical in engineering and detailing for glass structures. At this point, I was introduced to tri-pyramid structures, a fantastic, relatively small-scale custom stainless steel parts fabricator. This introduction was pivotal to much of the work I have subsequently done, and we have collaborated on hundreds of custom glass details since. They have a great ability to understand the multiple functions of connections and tease out the most efficient mechanism. I've learned much from them, and much of which is traceable in the engineering you will see shortly. The project in Seoul went very well, and the architect Raphael Vignoli invited DMP to support a number of commissions he'd recently won in the US through his studio in New York. I grabbed the opportunity to continue the good work we had done for them in Seoul and went to New York in 1998. The scale was significant compared to the projects I'd done in London, the majority being large-scale public or educational structures, and for this period, much less glass. One of the projects in which I acted as the lead engineer was the David L. Lawrence Convention Center in Pittsburgh, the winner of the institution's Supreme Award in 2004. The Convention Center was an important lesson in learning fast how to manage projects of scale with a significant number of stakeholders. The project was a complex one that essentially used a suspension bridge concept merged with steel megasystem to create long-span column-free spaces. And it was whilst I was working on this that I started to get very much more involved in the connections. And the connections are really where the magic happened, an area that I was personally interested in refining with the architect and developing giant nodes, transferring these large cable forces into these big steel frames. It was once while working through a detail with Raphael Vignoli himself that I was acutely corrected on a detail that I developed for the project. In fact, this detail. Perhaps naively, I had developed a large steel connection detailed fundamentally on the guidance of the US steel guides. The resulting detail was perhaps relatively easy to fabricate, but it was far from efficient in material usage and was basically ugly. Anyway, I presented this detail to Raphael. I could see his increasing frustration boiling up as I continually justified this ugly piece of detailing. Before long, he abruptly stopped me with a slam of his fist on the desk and said that I wasn't thinking about the elegance of the connection. So thinking I was being clever, I pointed out that it didn't matter because the connection was hidden from view and it would never be seen. This tipped him over the edge of rage and he started screaming at me in Spanish some words that I'm fairly sure were not compliments and surmised that it didn't matter if you couldn't see them because he could hear them. I never made that mistake again. Every detail deserves the same attention and the same rigor. And I think perhaps what Raphael could have more calmly referenced was this particular statement by Berthold Lubetkin. I met the architects Bolin Sawinski-Jackson shortly after working on the project in Pittsburgh and started working with them on a project in upstate New York in Corning, a specialist glass application company, if you know them at all. A company library that needed screening solution that protected its valuable books A contributor to its success was the connection development between the glass and the supporting frame. Again, working with Tripyramid, we crafted a node specific to its function and its relationship to the glass. And interestingly, the project included a very modest steel and glass stair. This then became an initial concept of what came next. But hold that thought for a moment. I met Brian while I was working with DMP in London in about 1995. He, along with Tim, was responsible for my understanding and interest in architecture. It was, and still is, Brian's passion. I learnt to share his love of architecture and building craft. It is a common thread that we continue to instill amongst the culture and in the culture of our practice today. When I returned to London in the early noughties, I felt it was time to do my own thing. I'd been keeping in touch with Brian, and one thing led to another, and before I knew it, I was working in his toilet in North London. A sharp contrast from the glamour of New York. Despite the conditions, there was a clear mutual interest in developing a practice that had an appreciation of architecture at its core and a core of its service, along with a clear approach that investment in research and innovation would someday define us. And so my top prize for influence has to go to Brian, because I am immensely proud of what we have managed to achieve since forming our practice, and I know that I couldn't have achieved it and managed it without his support and his counsel. So I thank you, Brian. And so to glass. My first meeting with Steve Jobs was a fairly intense event. Things never really calmed down after that first time. It was a whirlwind of excitement and challenges that propelled our team through a significant body of Apple work projects that exist today. Steve was fascinated by glass, and I was lucky to spend a lot of time working with him over the following 10 years until he passed away in 2011. He was an incredible talisman. His ability to inspire people was his real strength, and ability to motivate many to achieve the seemingly impossible. A very rare talent, and certainly someone who inspired me immeasurably along the way. And so to my journey with Apple began. And just to put it into context, this was the technology of the time. It was something that would ultimately change the way we lived our lives, and the technology that evolved from this continues to have immense cause and effect on the way we communicate today. The first project we worked on was in Soho in New York in Prince Street, the renovation of an historic post office building. And at core of this building and at core of this scheme was a staircase, centrally located about a symmetrical design. And it was key within the design that there should be a clear view, a clear sight of line for merchandising between the store, and to some extent that drove the stair to be glass. We trotted off to San Francisco, I remember this, not soon after 9/11, and we presented a model of a steel and glass staircase, which was fairly underwhelming, and Steve said as much. And he said at the time, why don't you just make it out of glass? And I didn't really know how to say no to him at the time. I hadn't really learnt the right protocol from saying no to Steve Jobs. So I just said yes, and got on a plane and went back to New York and started working on this particular staircase. In itself quite relatively straightforward, a simple structure of vertical glass walls and glass treads spanning between it. And what was important about it at the time was the use of new materials, and in particular the laminate that laminates glass together, laminate being the polymer that bonds layers of glass together. And this particular new material, Century Glass at the time, had been developed for areas of Southern America where hurricanes had been breaking windows and causing objects to fly through windows and causing damage to people inside. But what we'd spotted from this was the additional strength of this material and stiffness kind of led itself to the idea that it might be quite useful as a structure in structural glass. So we stumbled across this idea of thinking about laminating inserts within the glass itself, which allowed for free connection and meant that we could get away from the types of connections that we'd been looking at before, these holes in glass. And this insert technology started to become rather important in the sort of language of the staircases then evolved. Another key part to this particular material's properties was its ability in the post-breakage scenarios. So when glass breaks, we need to be confident that it can either distribute load in some way or it can carry load even in its critical failure. And once you have that knowledge, you can be far more ambitious with what you do with the glass because you're in that extra layer of safety that you hadn't had before with the materials that existed before. So we took these ideas and we welded them together in ways and we sort of refined a connection that was kept within the depth of the glass tread, and it was back to that idea of machining, keeping everything, making sure that every millimetre of material was doing something. So there was an intention to it, an intention to the development of this particular little detail that not only carried the load, allowed for the adjustment in the staircases, and it kind of led through from there to a series and a typology of connectivity that led to many of the staircases and bridges that we then developed for Apple thereafter. And it was the beginning of that journey, that beginning of our innovation in that material. And you can see here in Soho, it wasn't just the staircase, it became the bridge, it became the handrails, and it was extendable beyond many things. We're never always going to be doing a staircase in the same place, and in case this was, or the same environment. And this one, for example, in Los Angeles, at a similar time, soon after that first one, actually was a different structure. It was a series of glass panels hung from above, which then supported a glass treads in the same way, using the same fittings, but the ability of the connections was modified slightly so it could accommodate the lateral racking of the building in highly seismic loads. So it used the connection, changed it slightly to deal with the local conditions. And then in London, moving forward, we needed to develop something that would allow risers to be integrated with these glass treads, which was a code requirement in London. So we developed a further detail, a smaller version of that detail, which allowed us to connect risers to the back of the treads. So this carried on. We started to take this and extend it to different types of structures throughout the network and through the sort of development of Apple stores it was at the time. And this one in Nagoya was kind of interesting. It was the first in which we'd decided that we could possibly brave taking the glass panels from sitting on the floor and creating a beam and splicing them together with these similar connections to the ones we'd evolved and developed, but now demanding much greater loads out of them. More predictability. We had more satisfaction about how they were behaving, so we could be a little braver about how we're using them. And tying it together, each one of these treads to each horizontal riser with a modified connection so that we get a folding plate behavior and get a horizontal stiffness across the staircase itself, resisting those lateral forces that were from excitation from seismic loads, which are pretty prevalent in that part of the world. And into Beijing, a larger stair was required, and in this instance, broken up into 2 flights. It was too difficult to be able to do this in splice connections without them becoming too large, so we decided to hang it. And in hanging that staircase, we developed another detail which allowed us to pick up the load of each panel within the middle layer of the glass, again using those ideas of insert lamination, once again having more confidence in the behavior of those materials each time and each project that iteratively evolved. In Covent Garden, it was never always going to be straightforward to put it within its own space. In this case, it's combined with historic brickwork. So modifying those details to take accommodation of those different tolerances between the sort of inaccuracy of Victorian brickwork and the modern German fabricated glass staircase, a different idea of tolerances between the two. And it wasn't always going to be straightforward. Occasionally, it would have to be somewhat of a different geometry. And this project in Shinzaibashi in Osaka was the first of which used this curved glass. And the innovations in here was about developing or using chemically tempered glass, which allowed us to have a much better surface quality, which allowed us to laminate more than 2 layers of glass together to give us the stiffness we needed to resist these lateral loads and forces that this circular staircase was going to be subjected to. And I think it's important to point out at this time that a lot of what we've had to do over the time is modify, is to accommodate quite different design codes, very different forces in different parts of the world, different cultural attitudes to how you use glass, and at the same time maintain a very familiar aesthetic, because when you're inside the Apple Store and inside that retail environment, you need to know that you're in one of these spaces. So we were unable to do particularly custom ideas without deviating too far from that palette of materials and that typology. And in fact, reverse engineering through that is quite a complex thing to do, justifying what you already have to the codes you don't understand at that time. So very much, a lot about what we've done is about testing. Most of these early projects we've done, we've worked with Sealy in Germany, and they get very enthusiastic about testing things. Sometimes a little too enthusiastic, I feel. And that led to always moving on to different different locations, different staircases. This, for example, in 14th Street, which took that single story to 2 stories and relied on a single circular glass core and a series of glass beams that cantilevered fulcrumed through that glass core, which was acting as stability to pick up the external layer of glass. Now you can see here this started to become a bit of a trend, not my advice, to start putting, just before the store opening, everybody on the glass stair, jumping up and down and clapping, I call this structural engineer waterboarding. So these stairs started to take a language of their own, a little bit more sculptural, I suppose. They started to become the centerpiece of these retail spaces, which, was arguably detracting from the product itself. But it was how things were evolving at the time through the design team and then more waterboarding. But anyway, we moved on and we started to evolve and develop more ideas, and we were quite keen to take that development of each fitting and integrate it a little further. And this was a step where we were able to take that external fitting, get everything within the vertical load-bearing element and within the step itself, preserving the quality of that surface of glass, that quality of the material that we're so interested in pursuing. And so this evolved a glass material, an element completely laminated within the glass itself, so preserving the surface of glass. And in fact, once the point we'd started to make much larger glass, which I'm going to touch upon in a moment, we're able to integrate each one of those connections within a 15-meter piece of glass and go from those single panels of glass that we'd had before into one single piece. And here you have in Hamburg, the first of which is a 15-meter spanning glass stair stringer. Each bridge and each handrail balustrade was one single piece of glass with every single piece of fitting prefabricated within that element itself, preserving that surface of glass, just to see a little bit more waterboarding. And that version then replaced what we'd done in that original photo in Soho. It became quite successful. And it was about then that we started working with Foster & Partners on retail, and some really exciting things began to come from that relationship. And it was flexing our ideas and combining that of new ideas that I think really made something magical happen. This was a project in Zorlu in Istanbul, and it was the idea that really you don't really need to have another element to support the staircase when you've got a glass wall that also forms the envelope itself. So integrating this idea of reducing structure and integrating structure in building envelope and structures themselves, I think became an important part of what the next series of projects I'm going to show you are about. And in fact, where I find a real interest right now in trying to not double up and not have redundancy in other elements. That itself was extended here in Guangzhou, where we had 14-meter pieces of glass, each one again creating the envelope of the store, and laminated each one of these fittings within the glass, so you can therefore get no need for a structure supporting the stair when you have the glass wall there to do the same thing. I think quite a powerful message to be had there. Foster & Partners, in particular Stefan, had a very keen interest in refining further those details we've been developing, and in this instance, aligning them, making them more sympathetic to the geometry of the glass treads themselves, and calming them down, getting away from that sort of punctual fitting that we had before. And it started to really release the ideas that we had in glass and started to make it really sing. So over time, you can see it was a sort of iterative development of this typology as everybody had an influence on it, as fabricators understood more about what they could make, as we had more understanding about what we could engineer, and we felt safer about what things we could do. This in itself, to me, was about innovation. It was about that iterative development of solutions, developing over time. A seminal project for us was in 2006, with Bolin Sawinski Jackson for the Fifth Avenue in New York. This was, in fact, the entrance to an underground shop, and it created a sort of glass lantern to announce its entrance. Structurally, we were keen to have a glass structure and to also have it clad in glass in terms of the sizes that were available at the time. The challenge really was that a 10-meter by 10-meter glass cube is not easily achievable when a maximum piece of glass is 6 meters long, which was pretty much it was at the time in 2006, 6 or 7 meters, strengthened that is. So we took the idea along with BGT and CDAC, and we spliced 6-meter layers to 4-meter layers and interlocked them such that you would get one contiguous and monolithic piece. The challenge was that the autoclaves that were available at the time were only 6 meters based on the industry standards, and we need 10 meters. So we used aircraft wing autoclaves to make fins, glass fins, when they weren't making wings, and that enabled us to create this particular project. It then gave Mr. Seeley a very good idea, and he often went and bought a 12-meter autoclave. And with that, we started to experiment with much larger jumbo pieces of glass. Again, using the elements we could from taking 6 or 7 meter, 8 meter, and splicing them together to make larger jumbo pieces. This, for example, is a 15 meter by 3 meter piece in fabrication for this project in Sydney. And you might ask the question, well, why bother? Why don't you just, given it's all made out of glass, why don't you just put joints in it And really that was about the fact that we were maniacally in chasing transparency really at the time. And by increasing the number of by increasing the size of each panel, you thereby reducing the number of joints, and you're therefore reducing the number of fittings. And it's an important message, really, in terms of the design of fittings and the success of glass structures, because it is the fitting that you see. It's not the glass. So the energy and the effort needs to be equally balanced on the beauty and the elegance of that connection, the refinement of it, if you're going to make a success of a glass structure. Alternatively, have less of them, which is one way of doing it with much larger pieces. So this kind of double track was what we were always after. The logistics of that needed to come to pass, and it was very questionable at the time, developing larger scale equipment to move 15-metre pieces of glass around the world and put them on buildings. But over time, that's happened. And over time, there's now more than one place you can make this. There's several places in the world you can make 15-metre pieces of glass. The equipment now is fairly available in many different parts of the world, and that has shifted. That availability for this type of glass has become in more use, not just beyond Apple and way beyond that. So in New York, another example of a project which used a similar scale of glass, using similar ideas to create building space and transparent spaces. I think the next step for us was really when this project came along in Shanghai to develop a circular glass pavilion, 12 meters tall, but also to make it entirely from glass and with people in China for the China, and it was roughly around the time of the Chinese Expo. I spent a lot of time at that point going off to China and seeing lots of glass fabricators and trying to understand what they were capable of, and I stumbled across Beijing North Glass, who were a wonderful bunch of people. They had incredible enthusiasm and literally no idea what they were doing. So I went with the enthusiasm as being the most valuable thing that I could pick up on at that point. And we talked, and they said, it's okay, we can design a 14-meter toughening oven, and we'll have it fixed and ready in 3 weeks, in 3 months' time. And I looked at them, and I picked myself off the floor from laughing, realizing that at that point, this was twice the size of any tempering oven that had ever been built anywhere else in the world. I wished them good luck, and off I went. They called me back 5 months later and said, we've made it, come to Beijing, you can see it. So I did, and they had. And sure enough, they'd built this machine, which was able to then toughen and strengthen a 14-meter piece of glass in one piece. So no longer did we need to have this splicing idea. We could actually make it in single pieces. They learnt to laminate it to the quality we needed fairly swiftly, to curve it. And with that, we were able to then build buildings with, again, less joints and singular monolithic pieces, for example, this one in Shanghai, which, again, was an example of that mission and that drive towards transparency and using everything we could within the arsenal of fabrication, our engineering ability to do so. It came at that point, around 2011, that we had the opportunity to reimagine and redesign the cube that we'd built in 2006. And from that, we were able to take it from 90 panels of glass down to 15, using much of those ideas and technology that we'd developed and I've talked about before. So the larger glass, the integrated details, and in doing so, we could make a much more transparent structure, getting everything within the glass itself, protecting that surface reflectively, that quality of glass, and distilling that from what was from this level of transparency to this level of transparency in the same move. So I think this statement is somewhat resonates with me because it is about that point about keeping the details as refined as possible, because it is the elements that you see. So the next step was to make that bigger, and now we're able to make 18-meter by 3.6-meter tempered laminated curved panels. And a number of those have found their ways into projects around the world. For example, this project in Hong Kong, in Causeway Bay, which now has 16 meters by 3-meter panels of glass, until recently the largest tempered laminated panels in the world. And the projects with Foster and Partners, taking that idea, simplifying further, reimagining the way in which we connected the glass to really calm this down and really to make the most of the glass itself and really express the size and scale of the glass itself relative to the spaces, creating these really open spaces, allowing for these inside-outside spaces, harking along to the to the ideas of these internal town square type spaces that Apple were trying to develop, this kind of connection with the community itself. And this instance I particularly like, where we're able to take these large door frames which open and close over the space and use that in itself to stiffen the glass so we can avoid the need for any mullions, etc. So each time pulling a trick that kind of simplifies things themselves. So that, over time, was our march in size of glass as we went further and further through to 2000, 2015, 2016. And I want to talk about this particular project. This was really something that was particularly important to us because it was another shift in idea and another shift in materials. This was a lantern on top of a store in, and is a lantern on top of a store in Istanbul. And Stefan at Foster & Partners was very keen that we could find the simplest way we could to express this. So 4 pieces of glass was perhaps the easy and straightforward answer. We knew how to do that, 10 meters long, 3 meters tall. That was a bit of a no-brainer. How could we then put a roof on it? Now, we studied ways in which we would with glass, and intuitively, of course, that's where we started, and that's how everybody imagined it might be. But, of course, the glass could only be 3 meters wide, so to get 10 meters across, it wasn't really possible with a piece of glass without making it extraordinarily thick, or, in fact, looking at ways in which you support it. So, of course, there was ways you could do that. You could put glass beams in, steel beams, trusses, anything you wanted to do, but it all kind of jarred with the simplicity of these 4 pieces of glass, and it wasn't really satisfactory from that perspective. So Stefan was very keen to find something else, and it was with him and our team that we stumbled across other materials, and we started to look at composites, and in particular carbon fibre. And here you see Alex Thompson sitting on the fin of his yacht, which of course represents an industry that's been using composite fibres for many years in high-performance sailing, high-performance race bikes, race cars and the like. And it was with this that I guess we could make that leap from using it in that particular arena to that of buildings. And this was important because it meant that we could then develop this roof that was only 175 millimeters thick and spanned 10 meters and 50 millimeters thick at the edge, essentially imperceptible in depth. And this was a trick that, while rather simple to imagine, of course, the simplicity belies the complexity of how you actually achieve that. There's a significant number of forces that you have to accommodate through those joints and deflections and movements and etc. that have to be. But you can see by doing so, you can make this almost imperceptible structure, which is ironic because it then won the Supreme Award for structural engineering for a structure which seems to have no structure, which I think may be, to some extent, a recognition of that there is redundancy in a lot of what we do, and of course it's a journey in how you use materials you get to that point. So I'm being facetious to an extent. So there we go. So that's kind of, that journey to simplification came to that project in Zorlu, and I think that really what we were all trying to do at the time was to hark back to this particular comment, which I'm sure Mark Adams knows well. And it kind of led us to this next project, which, of course, when we were invited by Foster & Partners to be a part of, this is now known as Apple Park. It's Apple's headquarters in Cupertino. It's an enormous, epic building of great scale and of great complexity, resolved in some very simple and beautiful manners. But I'm going to focus a little bit, after I've just talked about some of the glass on it, on this little theatre, which is a little dot between the oblong-shaped and circle, called the now known as the Steve Jobs Theatre. But before we get to that point, I worked with Arup, who were the engineers for the building, and with Foster & Partners to develop ways in which we take this technology of glass that we'd developed through the retail world and how it would relate to this building. So you can see the adoption of these 15-metre, 3-metre panels meant that we didn't need to have any mullions in the perimeter itself. And that was super important for getting the connection between the inside and outside. And having been in there personally, it's quite a remarkable feeling to be inside that space and have no perception of your envelope, such that anything you see within the park space beyond is entirely within, feels as though it's entirely within your reach. The solar shades, these white glass blades, were a particular engineering marvel in my mind, developed by Foster & Partners and Sealy, where they're using a secret white formula, bonded to create, and then working with Gartner, who did an amazing job to put these on the building. So there was a lot of innovation that had come from that work in retail, had been baked into this, and yet again, this in itself started to develop lots of more new ideas. So it kept evolving. So the theatre, this is, in principle, the Steve Jobs Theatre. This is an early rendering of what it was imagined to be. And it was really, we were challenged with how we would figure out a way in which we'd create a 65-metre diameter glass building with a roof, and ideally without it being supported by any columns. Of course, you could have easily put some columns in, but it really wasn't the game. The game was to do it without the columns. And we came, obviously, having come through the journey at Zorlu, it was a little bit more of a relationship about how we could extend that. And working with the guys at F&P and with Premier Composites and with Freyner Reifer and with Celia and CDAC for the glass, etc., we developed these ideas of integrating the glass within the roof itself so that these forces could be translated and transferred from the glass, quite significant seismic forces, into the glass through to the base isolation that had been which was a very clever design by Arup, in which the glass sat. So the whole thing was a series of 44 segments of carbon fibre, fabricated and bolted together on site. So fabricated in Dubai, shipped, and then bolted together on site into this template you can see here. And in the background, you can see the glass ring. And then it was lifted in one single piece. And you can see it's almost impossible thinness for its scale. It's quite remarkable, particularly at this point. And then this was all done in one day. Makes it look easy, doesn't it? But I can assure you it wasn't. You didn't want to drop it. And then placing it gently onto the glass and connecting it and finishing it. And there in turn you had this most incredible space that allowed this connection between the inside and outside without that structure. Now, you will notice that there's lights and there's sprinklers in the ceiling, and every single one of those silicon joints houses a conduit that either has a light conduit or a sprinkler conduit 44 times around the perimeter. So in order to do so, that's how you serviced it without any vertical servicing or obvious servicing. The space itself required an elevator, and we had a little bit of fun here in developing a glass elevator that only had two stop, or one stop, but the stops were opposite each other. So in order to get into a cab, you would enter one side, and as you descend, the cab rotates on the helical rails that you see within the glass cylinder and deposits you out the other way. Needless to say, that was quite a complicated thing to build and fabricate, far more in that respect than perhaps in engineering it. So here we have this sort of march of projects, and we sort of took all these and we figured out that they all sit within the same structure in many ways, which has nothing to do with anything other than the fact that that happens to be the case. Somebody in our office was clearly too bored to figure that one out. So moving on, and more recently there's been some more developments and innovations in glass, again with Foster & Partners and different ideas, and it's always interesting to see what comes out of that creativity in the studio. But this was something about experimenting with very, very thin 0.5 millimeter marble laminated within structural glass to create these 9-meter panels themselves to create this incredible space, which it's not unusual to have glass laminated with stone, but to have glass laminated with stone when it is the structure and it's 9 meters tall and creates the entire envelope, I think was quite something. And very recently, in one of my particular favorites is in North Michigan Avenue, Apple in Chicago, where in fact this really quite incredible building just hovers lightly above this plaza and paying homage to this relationship between the town square and the retail space itself. This very lightweight roof engineered by Foster & Partners, and then the glass that we put between it, managed to design it so that we didn't have any mullions and no structure, so you really get that sense of internal and external space as a result of the envelope really doing its job to blur the boundaries between those spaces inside and outside. So I think the composition of it was particularly simple, but I think it lent itself very much to its purpose. And very recently in Milan, taking that idea of a glass box and to some extent the idea of a sort of Italian plaza fountain, using that as it relates to a space that you enter through in order to enter a subterranean store, which in fact is a sort of memory of the old cinema and auditorium that used to be in that space. And I believe it's a very well-used public space, and it's very, very great success in the city of Milan. So on to tomorrow's glass. Of course, this is kind of technology that we see today. And of course, a lot of glass has actually been a part of what we've seen in technology. We touch it every day. Our fingers run all over it when we're answering the telephone and surfing the internet, etc., on our social media. And my role as a professor of architectural glass at TU Delft, which I've recently started in earnest, a lot of what I have to do is try and understand where we are with the embryonic understanding of glass technology today, which represents the sunrise in the middle, and where we intend to take it. And these are the sort of streams that we're looking at. How do we develop thin glass? What uses can we use for it? Activated glass, how we can use it to communicate. Structured glass, how we can then further develop that. And, of course, energy and how we can capture it or reject it and, in terms of the use of buildings. Thin glass is kind of interesting. It's been around for a little while now, since the advent of the iPhones, etc. And we're still trying to find ways in which we might find it useful on buildings. We're quite interested in finding ways in which to use its flexibility and its strength in order to obviate the need for mechanical systems or mechanical hinges, etc., that would otherwise have been needed in glass facades. We're also looking at this particular pavilion, which takes thin glass and creates structure from it. This is early days. This is something we've designed and something that we're sponsoring and funding the development of as a prototype. And it takes the idea of very small pieces of glass, cramping them, and then holding them together by creating digital printed elements that we've printed in the office as prototypes, and sliding in these little joints and creating these kind of cushions, which in turn will create rigidity in this pavilion itself. So I think there's a system in there somewhere. I think there's something that might come out of it. It's somewhat prototypical, but it's got an idea, and I think it's got a life that we're quite interested in exploring further. Thin glass can be used in many other ways. I think the ways in which we might be able to combine it with acrylics to make more lightweight type glass, so you can get the effects of light, a material that's much lighter, but using the surface qualities of glass itself by using the glass as a veneer, or even using double glazing or insulated units on a much thinner version, so we can replace perhaps heritage buildings with thin versions of insulated units, therefore bringing their energy performance to a much greater than we can, perhaps when they're not able to be, not in a position to be able to change the frames, or in fact from a heritage perspective. And of course there's connections. This slide is something that we developed 2 years ago for Glass Tech, and really is a slight folly based on a project we were doing in Hong Kong, not a slide, but a facade project, and using these particular materials in order to be able to express an idea about connectivity, about zero metal connectivities using pure bonding and pure adhesives to do so. In this instance, TSSA, transparent structural silicone. And our project in London, which has been something we've been working on for a while, the Sky Pool, which came to us from Arup Associates and Hal Architects as a glass pool, as a concept, and we convinced ourselves, for many of the reasons that I talked about before, about the fact that glass was not really the right material to use, and in fact it would be better if we used acrylic, a little bit like a fish tank, and that way we could then bond it together into single pieces, into one single piece, and ship it from Colorado, which is where it's now being made, and lift it into the building in one place. So sometime this year, you will be able to see yourself, or somebody else, because it won't be me, swimming in this pool, between two buildings, which we're all very excited to see, but we'll see how that comes about. So as we move on to glass, I thought it was important to touch on circularity and sustainability, because there's an effect there which I think relates to some of the work I've been talking about, because of course there's a need for sustainability in some ways and how we shift towards that. We are all designing buildings in a world where there is limiting energy consumption increasingly drives the form of our buildings. Structure and materials innovations drove the identity in the 19th and 20th century, and energy is doing that right now. But even if we crack the energy problem, we still only have one Earth. Our resources at the surface are limited. Conserving those physical resources will surely become increasingly critical at every level of architecture and engineering design. Architecture is the most dangerous art form on the planet. A quote by David Adjaye in a recent Radio 4 profile of the architect. I thought on this, and I don't really see architecture as only an art form, and therefore I don't really buy into this slightly sensationalist comment. There is obviously a vital role for architecture being the conduit between the societal need for buildings and their responsible realization. That said, the impact of the statement is important. Buildings are a very energy-intensive activity. We all know that. Construction uses half of all materials used by people. If the cement industry was a country, it would be the third largest producer of CO2 behind China and the United States. We keep building because there is a need for growing population. Conservative estimates say that we will need to build 2 billion new homes before the next century ends. We also need to keep demolishing and keep rebuilding, often when there is no need. We have to positively address this issue of embodied carbon in buildings. The fact that we as engineers are a significant factor in the specification of a building materials means that we are complicit in this most dangerous art form on the planet. Clearly, I can't claim to be a sustainability evangelist through the work I have done to date. As I mentioned earlier, I was the facilitator of a building for the same glass building twice for no other reason than increased transparency and technology expression. But I have realised in recent years that enough is enough. There is a clear evidence that we have to change what we do and we have to do it faster if we are to arrest climate change. As structural engineers, we have been slow to react to this, typically seeing sustainability as the remit of the mechanical engineer in reducing life cycle energy usage through efficient renewable technologies. To address this, there is a lot of increasingly well-funded research into more sustainable approaches and materials for buildings. This is clear and very welcome. There is also an increasingly more buildings being completed that are beacons of that changing attitude towards material sustainability. We can all do more. We can all think harder about what we are specifying as it relates to the embodied carbon and push our clients towards more sustainable approaches. Of course, the costs dictate much of what we end up engineering, but within there is the latitude to at least ensure the options are clear and the sustainability reasons out from behind them are clear, backed by statistics. Over 18 million tonnes of glass is produced each year, accounting for 0.2% of total global energy consumption. With glass, it is actually very difficult to recycle into buildings and tends to be more energy consuming than it is to make it in the first place. So I'm more interested in repurposing glass and facade systems, adapting them and evolving needs. The sustainability of glass in buildings will be through innovations and solutions that address circularity. An established proportion of our R&D work is now funded by streams of revenue from tech companies. They are recognising that they have a responsibility with the resources they have at hand to stimulate and accelerate the sustainable approaches to their expanding building footprint and to extend that to the wider construction industry. An example we are currently working on is the development of a kind of kit of parts that allows the facade system to be constructed with a selection of modular elements that allow a degree of freedom in the design. They also have the ability to be tuned and controlled in terms of the embodied carbon content, a system that allows for a reassembled and adaptation and reuse without significant energy usage. Tomorrow's engineering. Computational power has released us, and we as engineers face the fastest changing landscape in how we develop solutions in the history of our discipline. Data is defining us as we find increasingly creative ways and uses for it. It is here to stay, and we must be embraced. We will see failure. We will see extraordinary progress as a result of the power that computational design now affords us. We must be brave. We must run as fast as we can, and we must use every ounce of our wisdom to keep us on the tracks of rationality. But at all costs, we must not block development and innovation with an attitude of restraint, or we will fall behind. Engineering has firmly moved on from the serial approach where we first estimate of structural sizing was either validated by a calculation or perhaps further refined by the reworking of those calculations. Now we first build a parametric tool to do all that for us, and then we allow the computer to significantly more accurately refine geometry, sizing, and performance simultaneously. It's no longer serial, it's parallel. I feel this step is as significant leap in how we design structures as was the first software analysis that allowed us to use the computers to analyze structural behavior. We can build on these tools ourselves with low cost of freeware, which provides access to a much wider audience of engineers around the world, which in turn will stimulate more ideas. It will stimulate creativity in engineering design. A project we are currently working on in Paris and our office in France uses the tool which was developed to analyze the structure and geometry, a lightweight biodome that really needs every ounce of efficiency leveraged out of the structure to keep it economic and magically transparent. Inputting the parameters and adjusting where needed, the tool will iteratively test the optimum structure within those set parameters. The speed and efficiency with which we can now do this means we can test many more ideas without having to go back to the drawing board. Testing design ideas becomes live and exciting and less of a drag. I am convinced that this results in more creative outcomes. Topology optimization, using computers to generate optimal forms and grid structures. I love this example of a connection developed by Arup, which in turn shows how this process can be where the process can develop a more materially efficient connection, which in turn, when printed, uses less material than we needed to achieve in the first instance. And these ideas, and this is an idea that's actually real, in Stuttgart, the University of Stuttgart have developed ways in which not only can they develop structures iteratively through parametric models, but they can also then weave it using robots and drones and create structures that are real. This is what we're seeing today. And as if engineering on this planet was enough of a challenge, we've recently found ourselves engineering on another planet in a competition for a Mars habitat sponsored by NASA. Along with Hassel Architects, we imagineered ways in which materials could be found on the surface of Mars and be sintered by robots acting as digital printers, forming a shell to protect inner structures and inhabitants from aggressive environments that you would otherwise find in there. It's tricky engineering with a material you have never seen on this planet. We all know engineering is truly wondrous. It surrounds us like a duvet 24 hours a day. It has a deep societal need and it's constantly changing people's lives for the better. But much more needs to be done to make that understood by a wider audience. The construction industry can be a creatively stifling environment where a true sense of value is often difficult to persuade our ultimate client of, but we should see this as a challenge and an opportunity. Increasingly, engineering is being seen as a commodity, something you just buy competitively based on price, a view that essentially places less value on what you provide and more value on your professional indemnity insurance. We have seen the concept of specialism around our subject grow to combat this drive towards commoditization, and I expect we will see more of this evolve at a grassroots level. We will need to do more at the same time in order to survive and illustrate the value. We as structural engineers need to get much better and persuasive at it if we are to reinforce the position we have in the process and to clearly define our value proposition. My most important job is to influence and inspire, just as those who I noted did for me in my career. I see it as our collective duty. It is imperative to the longevity of structural engineering. We need more engineers. We need to arrest the flight of those who study engineering and move to other careers. We need to communicate better about the incredibly fulfilling opportunities that engineering presents. Our value as a discipline depends on the quality of solutions and the service we provide, which in turn relies on the resource that is available from the educational system. Currently, in the UK, we face an annual shortfall of 59,000 engineering graduates to fill engineering core roles. Brexit will further exacerbate this resource shortage. Despite the headwinds, engineering is an exciting precipice right now, and something the younger engineers have an opportunity to take to the next level. I am excited to see where that takes us as much as I ever was. I hope I have the tenacity to hold on for the ride. Thank you. Thank you again for coming, and I hope that my enthusiasm for what we do is just a little bit infectious. Thank you very much. Thank you.
Wow. My goodness me. James, that was a treat beyond treats. Absolutely extraordinary. I kind of really am at a loss for words because of what you've just given us. What I can tell you is that you've just made an awful lot of people very jealous, very envious of the work you've been able to do. You know, I wrote down some words on a piece of paper, but really, that was extraordinary. I suppose what I take away from this is, yes, your enthusiasm, and I love what you left us with. That is it, where your job is to inspire the next generation of structural engineers, and my goodness, you're doing that. Your enthusiasm is clearly infectious. You spoke about how you were inspired by people, and at an early age, in fact, and how engineering became something that you just